Afternoon, everyone. This is Adele Newton. I'm the Executive Director of CSCAN InfoCan, and today it's my pleasure to introduce FAULT Kam, who is going to give us his presentation as part of our podium webinar series. FAULT won the Outstanding Young Computer Science Researcher Award in 2019. And FAULT, I'm going to just put it right on to you then.
Thank you. Thank you, Adele. And thank you, everyone, for joining and for the opportunity to discuss with you some of the work that I've been doing over the years. I'm deeply honored for the award. It's something totally unexpected. And yeah, I'm very honored to receive the award and to share with you some part of my journey. So today I will be talking about some of the work that I have done over the years with my collaborators to try to understand the impact of developer design decision on software quality. So when I first got the request for the talk, I was a bit torn about what should I be talking about. Should I talk about my life experience? Should I talk about my recent research? But then I decided to talk about this topic because I think it's what I've been researching for a longer time, and it's something I'm passionate about. So there will be a lot of design patterns, design smiles in the talk. I hope you find it interesting. So who am I? So I'm actually currently professor at Polytechnic Montreal, where I have this research chair with FAULT and Ivado on the quality assurance of software system, including machine learning based software systems. So my research is mostly around software architecture, design, maintenance, engineering of software systems. And more recently, I've been focusing some of my effort on making sure we can improve the dependability and trustworthiness of AI-based systems. So before becoming prof at Poly, I started a bit early on. I started in Cameroon, where I was born, actually. So I did my early and I also did computer engineering at Polytechnic. So I had these concurrent studies over a couple of years early in my undergrad years. I studied both pure mathematics and computer engineering, and then I did my PhD at University of Montreal. After that, I was lucky to move to Queens. I did my postdoc at Queens, and then it really kicks me out, moving to academia. I started as first an assistant prof in 2012 for Polytechnic Montreal, and then I move up over the years, and I'm currently full prof at Polytechnic Montreal. I'm fortunate to work with these fantastic students, which in my research group, and together we try to understand how people design software systems, how we can build better tools to help them design system more efficiently, to build high quality systems and improve the reliability, trustworthiness, safety of those systems. So these are really the brain behind most of the work that I do nowadays. But this is not what I'll be mostly talking about today. I will be talking about more flashback of what I've been doing prior to what we're currently doing today. So it's mostly the past years of my research work. Everything started during my PhD. So my PhD thesis was about pattern and quality object-oriented software systems. And I was fortunate to work with Yann, which is my inspiration in research. So he led me into research and taught me all the stuff that I know today. And Ian Gael was a passionate of design patterns. So I started my research looking at patterns. And that's how I evolved to look at the architectural systems and other designer architectural issues in software systems. So this is during my graduations in 2011. So we started on design patterns. So when I joined the research team of Ian Gael in 2006, he was focusing on understanding design patterns, building techniques to retrieve patterns in software systems. There was a big trend at the time that following patterns, which are good practices for designing software systems, we could actually more efficiently build systems of higher quality. So there were techniques to generate the code of systems from design patterns, retrieve patterns from systems. But at the time, it wasn't clear whether or not, beyond the expected benefit of this construct, we could actually always systematically build systems of higher quality. So when I started my PhD, one of the first questioning that we went in was to try to understand if every pattern is good in every context, whether or not there could have been side effects, whether or not we could actually provide more clear guideline on how to implement this solution to maximize the benefits. So the very first research project that I took on was to try to get the feedback from practitioners about the usage of this design construct in practice and their perception of the benefits of this solution. So this is young me, 15 years ago, when I was starting this study. So I embarked on this qualitative study to collect the feedback from the community of practitioners. So we built a survey and we try to understand how each of the 23 patterns that were cataloged in the Dyno 4, which at the time was kind of my Bible, impacted different dimensions of software quality. A study over a couple of months collected feedback, and to our somehow surprise at the time, the signal was that patterns could actually have an adverse effect on the quality of software system if not implemented or used properly or in the proper context. So this raised curiosity at that time in our research group about whether or not we should not try to quantify this impact and better understand the context in which they are actually having this adverse effect. And we published this more than 10 years ago now, and it was very positively received by the community. We got a most influential paper award 10 years later out of after this work. The reason we got this was because it's really went against what was the common law at the time. So at the time, people thought the design pattern by construct were good, and there were a lack of questioning of potential side effects that these solutions could have had on the design of system. So if there is one mini lesson from this first episode in my PhD for young PhD students starting in the field is really question common law. Never take for granted things that are intuitively expected to provide a certain type of effects, but always investigate deeper to try to see if there were some side effects. So from that early result, I decided to look broader on design construct and try to see what are the different type of design construct that occur when you build a system, and over the lifetime of the system, how this actually translate in good or poor design quality. So typically when you build a system, starting from a clean initial design, so this fancy car, consider you have all your good pattern in the right way implemented in. But when you start evolving the systems, fixing issue, adding new features, well, usually the design of the system start decaying. And as it decays, because of time pressure, because of external constraint of bringing the product to production, you end up doing suboptimal design decision, which introduce design defect in the system. And this is a bit extreme, but the design of the system can actually drift significantly. And the culprit from this, it's usually design smart. So you want to prevent this, and to prevent this, we wanted to identify those poor design decisions early on so that we can actually document their impact and provide clear guidelines about how to avoid those design decisions, or how to ensure that's the best decision that we made. So I decided to study design smells. What are design smells? The symptom of poor design or implementation choice. They were very popular at the time when I was doing my PhD. Martin Fowler was leading the effort in evangelizing the practitioners community about avoiding these design smells. And also in the research community, there were more and more attention of what this construct could actually lead and what the pitfalls of not sufficiently avoiding them or having them creeping the system. So design smells, example of design smells. So this chart sum it up. Usually when you build fast, you take poor design decisions. and you end up with poor code. Right? So the more popular design schema at the time was the spaghetti code. I think I'm sure many people in the design architecture community are aware of this. You have blotters, so you end up with long methods, so you have a large class. So this, at the design time, they sometimes appear to be optimal solutions, but they have side effect down the road. So we wanted to see how this smells could actually negatively impact the quality of the system and in a quantitative way. So that was the line of interest I had at the time. So a God class is typically a large class, control a significant amount of the behavior of the systems. It's now commonly agreed that it's a poor practice, but at the time it wasn't. There was still debate whether or not this could be appropriate in certain contexts or not. So we had to do a study to try to understand the impact of how to and provide some refactoring solutions. Another very popular smell was speculative generality. So early on in the design, you anticipate on the evolution of your system. So you take decision based on how you think this, believe the system will evolve, and you end up with this smell creeping in the system. There were debates whether or not they were good or bad. So Fowler and others, Brown, were proposing a catalog of these bad practices. And then they were conjectured to have a negative effect, right? But there were no quantitative evidence. There were no nuance in which context the effect were more or less pronounced, right? So I decided in my PhD to look at this. And I was lucky because at that time, when I was focusing on the problem, we were having the mining software repository movement, right? So we were having more and more access to open source projects that's were published. We had more and more larger repository. We didn't have GitHub that we have today, but we had SourceForge, we have other open source repository. And this repository provided information about the evolution history of system, right? So we could access the artifacts and we could actually replay the history of the evolution of systems. So for me, this would go. So then I decided in my PhD with my supervisor and other research team member who collaborate on the project to try to track these bad practices in systems, observe how they evolve over time, and try to look for correlation with design dimension, with quality attribute of the system. So we mined the repository of the system. We extracted information about the defect, the changes that were actually implemented on the systems over the years. We tracked, so we had detection tools to track this design construct. We extract them from the system, and we conducted a series of studies to try to see how they correlated with quality attribute. So one of the first study that I did on design smells after the study of design pattern was to look at how the smells impact the changeability of the systems. So to do that, so these are my vintage slides from back then. So I actually mined multiple versions of open source systems. At that time, we were focusing on Azure's and Eclipse. They were the usual suspect in the community at the time. And then I tracked the smells. So I extracted instances of the smells. I tracked them over time. And I conduct a quantitative study to look for correlation between co-occurrences of events, whether or not when a file was implementing specific smells, the odds of experiencing a changes in the future was higher or not. So I tested a couple of hypotheses, and to our interest or surprise at the time, we found that there were actually clear significant difference between making these theoretically poor design decisions and not making them. So files that were impacted by the design smell were actually significantly more change prone than files that were not impacted by the design smell. We also look at the different types to see if some correlated more or less with this effect, and we found that it was the case. So this was also a very interesting result at that time for the community. So when we published it, the community showed a broader interest, which encouraged us to pursue this line of work. And we look at the FAULT-PRONENESS. So we wanted to say, okay, this construct leads to more change because maybe they make the system more harder to understand, and then people have to repeat each rate multiple times whenever they want to implement a new feature on the system. But we wanted to see if this repetitive process also increases the risk of making mistakes, right, introducing failure. So we did this study to see if there were some kind of correlation between the two. And we found that this was consistent, and then the relation was actually strong. So this matters actually increased 30 up to 30 times the odds of having faults. So this was a strong message at the time. So it wasn't just theoretically, conceptually that we thought that they would have an adverse effect on quality, but we actually provided some early quantitative evidence that the relation seems stronger than we think. And some, especially coping-related smells, were actually more strongly correlated with the occurrence of defect, message change, for example. So this result was sparked an interest for this topic in the community, and then we won a most influential paper with this 10 years later. So I think it had some influence on how the community look at the impact of design smells on the quality of system. So that was the second piece of study. And then we also wanted, so currently we were looking at artifact exposed. So the system was built, we studied the history of system, and we look for correlation. But we also wanted to see what happened when people actually have to work on system containing those smells. We wanted to see if we could somehow measure the impact that the occurrence could have on the comprehension of the system. So I set up with my supervisor to design an experiment. We did some control experiment to try to see if when they occur in systems, by giving tasks to some practitioners, at the time we used students for the experiment, but some of the students we used in the experiment had some experience in professional software development. And we wanted to see if the tasks were harder or less, depending on the occurrence of this design construct, or whether or not the risk of mistake when they was higher. So control experiment 3, super control experiment. We use real systems, so we didn't buy system. We extracted parts of real system, and then we provided concrete tasks who were actually related to implementing features, fixing defects. So they had to do a real task that a developer would do in a normal context. And then we also asked for questions to measure the comprehension of the system. So the questions were related to understanding the behavior of part of the systems, to track concern in the system. So we built this questionnaire based on a taxonomy of common questions that professionals have to ask when they do maintenance and evolution activity. That was published by the team of Gary Murphy at the time. And then we ran the experiment and we timed the participant to the experiment. So we measure how long it took them to complete the task, and also we assess the accuracy of the task, and also we use this task load index to measure the perceived load, that mental load that is required to do the task. So we collected those indicators and we run the analysis. And what we observed was that individually, the smells were not making a big difference in developers' ability to complete the task, but when the smell were co-occurring, the impact started to be more pronounced. So this was an interesting result because it suggested that although you may have a goal, if you have only a single occurrence of the smell in the system in a period of time, but as this cripple in the system over time, the negative impacts start to increase significantly. So this work was replicated 8 years later on a more larger scale across 2 continents. So we had a team in Italy. We actually replicated the same study with a team also elsewhere in Canada, not at Poly, but Carton. So we had a more larger pool of participants. And then we tested the same question to try to see if the relation was sustained. And the results were actually confirmed. And this result also had quite some impact on our community because the early study, the initial study, we were lucky to win the best paper with that paper. And then 10 years later, we won a most influential paper for the paper. So it's part of the interest of the community and looking more deeper in this aspect of design construct. And later on in the talk, I will go a bit through some of the works that have been done by the community as a follow-up of this study. More recently, this is to work with one of my PhD students. When mobile apps became popular, and then we started to deploy software on resource-constrained environment, the issue of designing this software, this application in an efficient way started becoming a bigger concern. Right? So we wanted to see how we could support developers in guiding them to a more optimal design decision when creating those systems. This was particularly important because building an app at the time, at least in the early days, was not that difficult, in the sense that people who were building app were not necessarily professional software developers. So we had a more broader user base or developer base of people constructing app. And they were not necessarily opting for the more efficient design practices. So there was a need to ensure that we could actually document practices that are more adequate to ensure that they efficiently build the app. So we decided to look at energy efficiency, complement to our previous study on reliability, changeability, and others. And what we did at the time was profiling some apps, open source apps. So we did hardware-based energy measurements. So this was kind of a bit intensive as a study in the sense that we had to profile the energy consumptions of the apps over a period of time. And then we tracked design constructing the apps, right? So we detected the smells, and then we detected the mobile app specific smells, and then we isolated the effect of each of the smells on the energy consumption by playing scenarios with the apps and profiling the energy consumptions over the years. And what we observed in that study is that actually these smells also had an impact on the energy efficiency. Some smells resulted more quicker battery drain versus some other smells. So we cataloged those results and published in the community. We also got some of the attention. So this was for the impact, the relation or correlation between the occurrence of the design decision and some quality attribute of interest. One thing that we wanted to understand now that we knew that these practices were actually having an adverse effect on quality was to try to understand the context in which developers make those decisions, right? How are the smells introduced in systems? What can we do about it, right? How can we prevent them from getting in the system? So we did a study to we tracked the birth and evolution of God classes, and a similar study was also pursued by another team in the research community. What we observe is that usually the smells are not the result of a decay of the architectural system. They are actually, most of the time, result of initial design decisions. So they are born smells. And this was a bit intriguing because our hypothesis at the time when I was starting my PhD was that the smells are mostly a result of architectural decay. So as the system evolves, as we are making changes, as the knowledge is eroding, we tend to do poor decision. But these results show that in many cases, the decision were taken upfront. And then many cases, they were actually introduced during maintenance activities. So when people had to fix an issue or evolve the design of the system in a specific way, those were, according to our quantitative studies, those were the period in time where they were actually more likely to introduce those systems. We also look at removal to see if there were a natural tendency from developer to remove those smells from the systems. And the result was, and what we observe is that these smells are not systematically removed from the system by developer. Usually when they are removed, it's actually accidental. The portion of refactoring, which is actually the activity targeting those smells, it was very, very tiny. And this result was confirmed by another group, very nice paper that occurred 4 or 5 years ago, where they actually conduct a large-scale study surveying the refactoring practices of developers across different continents. And then they found that developers actually don't refactor for smell removal. Smell removal appeared to be a side effect of this refactoring activity. So this study suggests that probably need more guidelines and more tooling, right? In our perception is that we need to make the process of removing the smells as easy as possible by automating this process as easy as possible to support and increase the likelihood that developer will actually remove those smells from the system. So this was code smells, right? So we look at code smells, which are the direct result of developer design decision, the intents, they make decision, and then this decision is translated into code as concrete implementation. And then we have seen that they have actually a concrete adverse effect on the quality of system. But the idea of smells is actually more spread across the development process of software systems. So we don't have only design smells or code smells actually. So after these initial studies, there have been a large interest in the community practices in all other aspects of the development processes. So there have been test smells, which have been studied. And similar to code smells, they actually have a negative impact on the maintainability of systems. So those practices have. So linguistic smells, this is something we studied in our group as well a few years ago, which are related to the naming and commenting, naming of identifier in the codes and the equation between the description of the behavior of methods in the code, the consistency and the inconsistency that you can have in the code. Right? And these smells actually have a negative impact actually as well on the quality of the system. There is a team in Europe who actually look at SQL smells, right? We also have a recent study that we did this year and try to see how these SQL smells actually evolve and interact with the code smells in the code. And those practices have also an adverse effect on quality. Teams have looked at smells, the architectural, like the MVC type of design of the systems. So there have been smells in service-oriented systems. This work actually also showed that they still increase the change proneness of the system. Other studies are also look at energy efficiency. More recently, there have been work looking at infrastructure, so the automation of the development pipeline of the system, result also in bad practices that can have an adverse effect on the overall quality of the system. Recently, there have been work looking at community smells, which is actually how the organizations of teams, right, impact the quality of the product that they're building. So there can be smells even in the way we structure the work interaction in the company. So there have been some studies looking at this aspect, going a bit beyond the code and looking at the social technical aspect and how some smells in the way that the teams are organized have a negative impact on the quality. In my team recently, we have been focusing on machine learning-based systems because they are now ready for prime time. So they have been integrated more and more in production code. And we look at practices, right? We look at the design practices that developers are following when integrating those systems. And we found also that smells and clones, we had type of smells, are more prevalent in the implementation of the system than one could actually have imagined. So in a recent study, we attempted to quantify the effect of these design smells, the code smells in the deep learning project by similar to what we did 10 years ago. We mine the repository of some deep learning project, extracting the artifacts, extracting information about false occurrence in those systems. We track the occurrences of the smells in the systems, we track the evolution over time, and then we look for correlations between the code smells in the deep learning codes, and in our case, the quality attribute of interest was the bug proneness in this study. And what we found is that first, the amount of smell is increasing over time in the system usually, which means that despite the body of knowledge that we already have on the negative impact that code smells can have on the quality of systems, developer working with this new technology doesn't seem to be aware of the adverse effect that it can have on the quality of the system. So there seems to be the amount of smells increases versions after versions from the system that we studied. And it's an increasing trend. And then we spot very few refactoring. So refactoring doesn't seem to be the main focus of design of the system at the time. We look at co-occurrences with defect, and similar to what we have for traditional systems, they also correlate with defect. So design smells in ML-based systems are also having an adverse effect on the relative system. And this is important because more and more industries are trying to integrate ML-based system in even critical domain. We're trying to use them in in image recognition to derive some diagnostic. But if the implementation of the logic of this model is flawed or it's crippled with code smells, which increase the risk of faults occurring of those smells, well, there is a likelihood that we may end up with application that can have a very negative, very critical, catastrophic impact when the defect actually occurs in production. So more care should be taken. And one thing we also observe is that when we had smelling files, the time to fix the defect was actually higher. Right? So they don't only result in faults increasing, but they also increase the maintenance overhead. Right? So it takes more time to fix the fault when the faults are in the system. So one takeaway from this is that bad practices are everywhere, right, in the software development cycle, and there is a cost for that. Right? So they may look at efficient, quick, early solution to a problem, but there are side effects on the quality of the system. Right? And they increase maintenance costs for those systems, because if they're making every bug fixing or evolution activity longer, then there is an additional penalty. So that more attentions need to be given to those practices. Currently in the community, we are proposing smell detectors. So we're building tools to allow teams to track them, but it may not be the more efficient way to cope with the problem, because when we track them when they're already in the system. Right? So there should be more effort preventing the bad decision to be made, to be taken upfront. Right? So we in my team, we are looking more in that direction now to try to see how we can detect the potential decay or predict a potential occurrence of this poor construct in the systems, and also automate the removal. So we're proposing search-based techniques to try to automate and restructure the code to minimize the cost of removal of those solutions, poor solution from the system. Since, as we have seen, the removal of code smell doesn't seem to be the higher priority of implementing at this point. So these are two takeaways that I would say from my experience looking at this problem. In general, the magnitude of the phenomenon, it depends on the point of view, right? So the context is always important to judge whether or not it has a significant effect. As we have seen through the different studies, not all smells have the same pronounced effect on adverse effect on the quality. So it's always important to them to context, help prioritizing the decisions when team has to cope with them. And so that's it. That was my story that I wanted to share about how we look at the impact of these practices. So good practices in theory sometimes can translate into not so good practices in practice. So it's important to investigate this effect and to track for them. Bad practices have a pronounced effect on quality, and the smells are everywhere, and they should be taken into context. And we need more tooling, more proactive tooling to prevent the poor decision being made instead of just acting on the decision afterward. So I hope I have time for some discussion, some questions, and I will be happy to interact with the audience.
Thank you, Futse. If anyone has any questions, they can put them in the chat or raise your hand, whichever you prefer. We'll wait a few seconds to see if anyone has any questions or comments on the presentation.
It could be
I don't
about
see any
my
right
research
now.
experience as well. It could be about anything.
Of course. That's right. We have some time still, obviously, on the call. Does anyone have any comments, questions, discussion? It doesn't look so, Futse, so I think we're going to be finished early, but thank you so much for your really great talk. As I said, this one will be, has been recorded and it will be uploaded to the CSCAN website for everyone to see. And again, I want to thank you for your time and for your presentation. And thanks everyone for attending. Thank you very much.